Explain the use of JFET as a voltage control resistor. When JFET is in ohmic region, it acts like a voltage control resistor. That is, by changing the voltage, we can control the resistance between drain to source. Voltage has to be changed in between gate to source. Now, for given VDS, what will be the voltage is can be calculated using a graph of ID versus VDS. For example, if when the VGS is off, you can see the graph shows that ID is directly proportional to VDS and its inclination decreases as we increase the VGS in negative. Okay, the voltage VDS is reversed and curve obtained for the low voltage values of VDS, they are found almost symmetrical to the first coordinate. That is the explanation for voltage control resistance as JFET as a voltage control resistance. The next question is JFET. It's a numerical question. The JFET has GMO equal to 6000, IDSS equal to 12 milliamp. Find its drain current at VGS equal to minus of 2 volts. The square law formula ID equal to IDSS 1 minus VGS divided by VGS of raised to 2. GMO is equal to minus of 2 IDSS divided by VGS of. We will calculate GMO by this formula. Right now we just need a find its drain current, that is ID equal to IDSS 1 minus of VGS divided by VGS of whole square. Why we need to find the GMO? Very simple. We don't have been given the value of VGS off but the value of GMO. Now using this equation we will find VGS off equal to minus of 2 times IDSS divided by GMO. That come out VGS of equal to minus of 4, and when we substitute the value of VGS of in the equation we will get ID equal to 12 milliamp. Explain the construction of N-channel JFET. Explain its working using the drain characteristic and transconductance curve. Show that GM equal to GMO 1 minus of VGS divided by VGS of. We will start the question by drawing the JFET schematic diagram. N-channel JFET with the P side gate. Both the P side gate are attached to each other. One side is named as a source and a P side slab. Second side is known as a drain. Now construction. N-type silicon bar containing two PN junction at the side. Bar form the conducting channel for the carrier. The bar of N-type is called N-channel JFET. Two PN junction was formed. The diode that connect the internally and common terminal called gate, and which is taken out. we got three terminals. One is gate, another is source, the third one is called drain. Thus the JFET has a three terminal: gate, source and drain. Fourth terminal is subtract, which we do not use, and usually we keep it to the ground or in air. Okay. Now working of the JFET. When the voltage VDS is applied between through drain to source is positive and gate to source as a negative. If we do not apply any voltage between gate to source, let VGS equal to 0, maximum current will flow between source to drain. As we start increasing VDS, the current will start increasing, but at the peak it reach. After that peak is called V pinch off. After that the current will not increase no matter how much we increase VDS, because the channel width is fixed. The number of carriers that cross the channel is limited by the deflection region between the diodes, these PN junction diodes. Okay. Second, if we apply a small gate and that gate voltage is negative, this deflection region increase inside the channel and we will get ID less at the peak. When the reverse voltage VGS is applied between the gate and source, the width of the deflection region increase. This reduces the width of the conduction channel and thereby increase the resistance of N-type bar. Consequently, the current from the source to drain decreases. If reverse voltage at gate is decreases further, the width of deflection region increases, and so as the channel resistance increases, channel width decreases. Automatically that result into the less ID current. The drain characteristic shows the drain characteristic is ID versus VDS at different VGS. As you can say, VGS minus 1, minus 2, minus 3, minus 4, minus 5, and one more VGS has to be shown over here is minus 0 volt. Okay. The curve between the drain and ID currents and the drain to source voltage is called actually drain curve. There is three region in this drain curve. One is ohmic region, active region, saturation region, and breakdown region. Okay, in ohmic region, when VDS is less than the critical voltage Vp, that is called the pinch off voltage, the current is proportional to the voltage and shows the ohmic resistance of the device. At the constant current region, that is called saturation region, the VDS, no matter how much you exceed the VDS, okay, after the VP, the current remain the constant. Breakdown region, if IDSS exceed a certain critical value, the drain current suddenly increase due to the breakdown of the reverse bias junctions, PN junctions. This is the breakdown region. Cutoff region, as VGS become more and more negative, the drain current decreases. At VGS minus 5 volt, the drain current almost zero. This voltage is called gate to source cutoff voltage VGS off. Transconductance curve. This is the graph of ID versus VGS. The curve between the ID versus VGS is called transconductance curve. That means 1 upon of resistance between ID and VGS. Okay. Now the curve is non-linear because the current increases faster as the VGS approach to zero. The two important points is that finding the Shockley equation, okay, ID equal to IDSS 1 minus VGS divided by VGS of or VP the whole bracket square, okay. Transconductance, that is GM, is given by is defined as change in ID divided by change in VGS. If we differentiate the ID equation, we will know the value of GM. Therefore, GM equal to, okay, d by dt of IDS is a constant, it will take out 1 minus VGS divided by VP whole square. When we take the derivative of these square, 2 will come 1 minus VGS divided by VGS. Inside the bracket, we will derivate 1. 1 is the constant value, it result into 0. And the second time, VGS divided by VP result into 1 minus 1 upon VGS of minus will be outside. So the resultant we will get this equation. Okay. If we rearrange, we will come across, okay, minus of 2 IDSS divided by VGS of 1 minus VGS divided by VGS of. This term is known as a GMO and remains same. Okay, the GMO is the slope of the tangent at the point on the transconductance curve where ID equal to IDSS. Now this is the numerical question. Determine IDSS has given, GM is given. Determine the value of VGS off and estimate the GM. Okay. So to determine the value of VGS off, we will use GMO equal to 2 IDSS divided by VGS off. VGS off will be equal to 2 times of IDSS. And by knowing the value of VGS off, we can easily find the GM value. Sketch the cross section of deflection MOSFET and explain its working. Draw and explain its drain characteristic and transconductance curve. Now, MOSFET metal oxide semiconductor field effect transistor. Metal oxide semiconductor field effect transistor. We will draw a schematic diagram of that. You can see. Okay. For P channel D MOSFET. Okay. Metal is the gate, oxide is the oxide layer, and the semiconductor is the N channel. Between this form the metal oxide, and the remaining concept is the field effect transistor, which already we have somewhat discussed. P types of subtract constructed at the channel between the drain and source so that a small passage remains to left and the electron flowing from the source must be passed through the narrow channel. The systematic symbol for the deflection MOSFET is this. Working since the gate is negative, it means the electrons are on the gate. Okay, when gate is negative, more electrons will be pushed inside the channel, leaving the layer of the positive ions on the part of the channel. In the other word, the empty n channel of some of its free electron, therefore the less number of electrons are made available to flow for the current to flow between the channel. The greater the negative voltage on the gate, the lesser the current flow from source to drain. Thus, by changing the negative voltage on the gate, we can vary the resistance of the channel. This is called deflection mode of the MOSFET. Drain characteristic of the D MOSFET, as you can see, it can operate in positive voltage VGS also, in negative voltage of VGS also. In negative voltage, it is known as deflection mode. In positive voltage, it is known as enhanced mode. In enhanced mode, when the gate voltage is more positive, what happens? The channel is substituted. That means it is feeded more and it tried to enter into the P channel. The width start increasing in the P channel and more electron able to flow since the channel width increases. Transconductance curve of the metal oxide, deflection region, enhance region of D type metal oxide field effect transistor. Draw construction of enhanced type metal oxide semiconductor transistor. In this, there is no channel. We have to create the channel. The diagram is wrong. Okay. Here you have to create the channel. Okay, this P is completely covered from this point to end of this. Okay. I will show P type metal oxide semiconductor. Sorry, N type enhanced